So today we're going to actually solve for a deflection of our simple end-loaded cantilever beam with a fixed support. So to do this, I would definitely highly suggest to look at your Lecture 8 Mathematica notebook. So let's download this right here. Let's open it up and let's get to solving this fourth order ODE. So when I'm end loading, I can model a non-distributed load as a Dirac delta function. A Dirac delta function basically is zero everywhere except when inside of that delta is equal to zero. So that's how you can model essentially point forces in your function. So that's a nice way we can solve the problem. So I've already got this set up for you here. Functions, you look at our initial conditions and boundary conditions. Again, at x equals 0, no deflection, no change in slope. At our end load, we're going to have no resultant moment, but there will be, at x equals 0 as well, there is going to be a resultant force, a shear force specifically. So y times I. You notice here that it's not negative because, again, you have already the negative built in there. We're going to solve the function here. Let's go ahead and simplify it. I'm getting rid of any heavy side theta setting equal to 0. And that looks pretty good. We see the beam maximum deflection value. Again, for those loads, we can see our shear diagram. Constant, makes sense. Moment, maximized at x equals 0. This looks pretty solid to me. Looks very similar to our derivation we did way back in the day there. So it's really critical. Again, the key to solving these problems is establishing your load correctly and establishing those boundary conditions. And then checking, does your answer intuitively make sense with what you know the system to be? So that's really, really important essentially as you go about and try to solve these problems. So next time we're going to go to 3-point bending test and solve it in Mathematica. See you then.